Good morning, everyone. Welcome back to Physical Geology 1403. We're going to be picking up today from where we left off when I had to end a little bit early last time. So I have a couple slides left on this PowerPoint, and then we'll move on to our newest lecture. My wife sent me a video on Instagram yesterday and I don't know, I may have told y'all how I feel about like social media. I don't really do it. So I don't have Instagram. So whenever she sends me something, she has to text me the link. And then I open it on the Instagram website. And then I have to accept that I don't want to download the app and I want to watch it in the browser. And it's a whole deal. Usually it's not worth it. But this time it was a video someone took of a car like nosediving, like a sinkhole forms under the car in the parking lot. And it like nosedives into the sinkhole and gets sucked into the mud, and the car's just gone in like 10 seconds. And the caption was "Geologists on their way to work." I loved it. Yeah, it's a great one. That's a good one. Right. So I thought that was appropriate because sinkholes are a part of what we're talking about today in the remainder of this lecture. Before we begin, though, any questions? How was my Valentine's Day? Yeah. Well, we didn't do anything. We agreed months ago that we wouldn't do anything for Valentine's Day because we're in a bit of a financial tough spot since I'm paying tuition again. All of our money that previously went into doing things like, hey, it's a holiday, let's do something fun, is now going to the University of North Dakota. So we just had dinner at our dinner table, which is actually a rare circumstance. Most of the time, one or both of us are taking care of our kids' dinners and cleaning up the house at the end of the day and stuff during dinner time. And so one of us eats and then the other one of us eats. We both eat, but we're exhausted, so we don't do this big thing at the table. So we're just scarfing our food while we watch an episode of something on the couch and then go to bed, something like that. Or she goes to bed while I do homework, actually. That's how it goes these days. So actually having dinner together with, a nice glass plate with our food on was at the dinner table. That was actually a really nice evening. So that's what we did.
Are you a firm believer that Valentine's should be every day, at least with your significant other?
Should Valentine's be every day?
Yeah. Like the philosophy of like loving your significant other like every day as you would Valentine's.
Of course, I believe that you should love your significant other every day. That is a fundamental tenet. That is a fundamental tenet of a relationship. Here's a bit of free advice. If you're only focused on loving your significant other on Valentine's Day and you're not trying to make them feel it every day, that relationship will not last long. Okay?
How long were you married?
I've been married, let's see, in August. Yes, how long have I been married? It's okay. How long have I been married? This August will be 9 years. Thank you for that. I don't look old enough. I appreciate that. 9. 20 years. No. I turned 30 last year, bro. I haven't been married since I was 10. No. We got married shortly after we both turned 21. Not shortly after, like we were 21 and a half. She's 1 month older than me. I tease her that she's a cougar. She hates it. Okay. Any other questions? I'm totally fine answering questions that aren't necessarily related to the class, but we used a lot of time in our last lecture talking about black holes and time and the speed of light and stuff, which is fascinating. Probably won't spend too much time talking about those subjects right now, but if you have questions about that, we can talk about it later. If there are no questions about anything else, let's jump in. We left off at groundwater. Oh, actually, really quick, you're getting lecture 9 today. You're getting lecture 10 on Tuesday and lecture 11 on Thursday, okay? Which means that your exam over module 2 is going to be the following Tuesday. We will have a review for that and everything, Okay, so it'll be Tuesday of week 7. You will get the lab exam Thursday next week. 1 week from today, you will get your lab exam. We will have our lecture 11, and then after lecture time is over, that's when lab time begins. Now, you can feel free to start your lab exam here. For those of you that are here in person, you can do your lab exam here. I have physical copies of the exam set for you that you can do all of the tests and things that you've learned how to do in the class. You can do those here. For my online students, it's just the same format that you've been doing, right? You've got videos for each lab exam sample, and you can watch as I do the test for you, and you can make the same observations that the students here do. It's entirely up to you if you want to stay after class to take the exam here, or you want to do it online from home. It's up to you.
Wait, is that exam time?
Yeah, all of the exams have to be timed. I don't have a choice in that. But again, I give you a maximum time limit. You can stay here for the entire 500-minute duration of the exam that you have available if you'd like, or you can go home and take advantage of the same time limit. You'll know that you're welcome here at any time, right? My online students, that applies to you as well. If you want to be here at any time, you just need to ask. Okay, so just prepare yourselves mentally for that 1 week from today, lab exam. And then that following Tuesday, 5 days later, exam 2 over module 2, lectures 9, 10, and 11. Sorry, 8, 9, 10, and 11. Okay, we all clear on that? And then remember, we do not have our class movie night on the 23rd. I had to move it to the 1st because of a family matter that my wife informed me of. Huh?
Because I went off this and I was about to.
Oh, you preferred the 1st?
Yeah, because I'm gonna be out of town.
You're going to be out of town? Okay. Oh, great. Yeah. Please come on the 1st. We'll have a good time.
Yeah.
All right. Let's jump in. Groundwater. We talked about running water last time, right? Now let's talk about groundwater. There is a big misconception about groundwater that when I say groundwater, a lot of people tend to think of underground rivers, like an actual body of water that exists underground. That is not the case. You guys ever heard of a dowsing rod? Yeah, you know what this is? Tell me what that is.
Well, dowsing. I know a couple methods. I know there's one where you've got the two metal rods and something about magnetism of the water when they cross you over.
Right. Okay. So the way that a dowsing rod is supposed to work is you've got these guys who claim to have the ability when they're holding 2 copper rods to sense when there is water underground. And so they've got 2 copper rods, and they'll walk around, and they'll say, "Oh, there's water here. Dig a well." And then people dig a well, and water comes out, and oh man, this guy's legit. It's been around for a long time. I actually had someone in my class whose grandfather, that was his career, and she was all about it. She was like, "This is real." It's not. Guess what? You dig underground anywhere, you're going to hit water. That's groundwater. It exists beneath us pretty much anywhere you go. Granted, there are some places where there's more and some places where there's less, but it's not like there's one massive river underground that you can tap into by using 2 copper rods to somehow magically figure out where they are. It's hocus pocus. Okay, I'm just going to lay that straight. All right. When I say groundwater, what I'm talking about is the water that occupies the pore spaces between grains and sedimentary rock. Remember, your sedimentary rock is sediment like sand that's been compacted and cemented, but often still has just a little bit of empty space between those grains. And when you fill all that little bit of empty space in a huge body of rock underground, it can hold an incredible amount of water. That's what groundwater is. Now, this is also, the water that is in the ground can also be an important source of chemical weathering and transport of dissolved minerals. Okay? That's actually how we form caves. How many of you have gone to my YouTube channel and seen the videos I made about caves?
I've got YouTube channel to do work like caves.
Okay, it's Hard Rock Geology, HARDT space rock space geology. Okay, I have a bunch of videos on there of caves I've gone into, and you can see some incredible things there. But I actually also, they're like in presentation format, so I have clips and videos and live stuff of me in the cave, but then I also, I go to a PowerPoint I made that explains how the cave's formed and why, and where they are, and all of that sort of stuff. So basically what happens is you get some form of acid, like a carbonic acid or sulfuric acid, just like you would from acid rain, but it forms underground, okay? Certain things can dissolve, and in dissolving into the water, change the pH level of that water to be more acidic, which in turn causes more things to dissolve. When that happens, you get caves underground because it's dissolving away, usually limestones.
Like Carlsbad.
Carlsbad is a good example. The Carlsbad cave network is the product of sulfuric acid moving through a limestone bed. Yeah.
And then also, like, especially if there's like a lot of water in these caves, it can support entire ecosystems of caves, like deep cave ecosystems.
Yeah,
like,
there are-
you get endemic species of like blind crawfish or reef salamanders only live in that one cave.
Many cave networks do have pretty complex ecosystems, and they can be very fascinating. And I show you some of those things in my videos as well. I show you cave scorpions and cave crickets and fungi, and there are some dead things I found, most of which aren't supposed to be there. At the bottom of one cave that I made a video of, there is a 12,000-year-old, there's a skeleton of a 12,000-year-old short-faced bear. Yeah. So there's cool stuff, okay? When I say pore space, this is what I'm talking about, okay? The spaces between the sediments are what we call pores. The more porosity a rock has, that means there is lots of pore space available. That means that it can hold a lot of fluid. The more porosity, the more fluid it can hold. When I say permeability, that's how easy it is for fluid to transport from pore to pore, aka flow. So if I have a rock and I describe it as having high porosity, think it's holding a lot of fluid. If I then say it has high permeability, that means a lot of those pores are interconnected, like you have over here, and therefore that fluid can flow from one to the other, and you get groundwater movement. Now, if I say low porosity, low permeability, that means none of those things is happening. If I say high porosity and low permeability, that means that it can hold fluid but not move it from one pore to another. Okay? Both of these are very important when it comes to determining rock types and layers that can and do hold water. What else might this be relevant for? Any ideas? What other fluids are we fond of taking out of the ground? Oil. Porosity and permeability are an extremely important part of analyzing rock to see if it can in fact hold oil. Okay? If it has oil and it is permeable, we can get it out with little issue. If it contains oil but no permeability, the oil is there, but there's just no natural way for it to move, and therefore we can't pull it out, that's when we frack it. Fracking is essentially fracturing, breaking that rock layer up, which is containing oil, and artificially making permeability to allow those hydrocarbons to escape. And where do they escape? Upward, through the tube we stuck down there, because they are more buoyant than the water we pumped down there to frack it. Make sense? So porosity and permeability, very important, okay, in many ways. Now, when I say groundwater, thus far to us that has meant to a certain point underground. When you get to a certain point, there is water in the rock, right? Well, that point, that sort of surface below which there is water in your rock, we call that the water table. Have any of you heard that term before, water table? The water table is essentially a surface that exists underground, below which your rock is saturated with water. If you want to have a water well that it runs consistently at any time, it's not reliant upon seasonal flow of water. You need to put it below the water table, okay? A well that stops here will not give you consistent sources of water. A well that goes down here below our water table will give you water year round because that is saturated rock, okay? Now, depending on where you are, the water table may be really deep or really shallow. A generally good idea of figuring out if you're close to your water table is how many lakes and ponds and stuff do you have lying around, okay? Because remember, these bodies of water are going to try and get close to the water table. Rivers, streams, weather their way down through the rock until they reach approximately the water table level. Because below that, they can't flow below the water table level or else the water will come out of the rock, right? That's essentially where they try and end up. So if you've got a lot of lakes and streams and ponds and rivers and stuff around, you're probably fairly close to the water table. You probably don't have to drill very deep to reach it. But if you're in a very mountainous region, right, water table's probably pretty deep. You're probably pretty high up above it. And so you'll need to drill a deeper well. There are some circumstances that exist which prevent you from having to go so deep, though. Okay, so say right here in this example, let's call this rock sandstone. Okay, this rock is sandstone, usually pretty porous. Depending on the type and certain other characteristics, it can be pretty permeable, right? Great for holding oil and water, sandstone is. Okay, we like sandstone in the oil industry and we like it in the hydrogeology industry. Okay, but right here we've got a lens. Okay, so a kind of truncated layer of clay could have been deposited by a flood, or perhaps back when this rock was being deposited, there was a brief moment of rising sea level, which caused clays to be deposited instead of nearshore sands, things like that. Any number of reasons why you might end up with a layer of clay in these layers of sandstone. But whatever the case is, here you've got clays which prevent water from passing through them, right? We've already learned about that. And so you get a storage, a buildup of water on the top surface of this clay within the sandstone up there. It can't pass through the clays to reach the rest of the water table. And so you've kind of got this, what we call a perched water table right there. On top of this clay layer, we would call that an aquitard, okay? It's preventing the passage of that water. It's an aquitard. And so a lot of the time, what you'll do if you're in a high elevation area, like you live in a mountain range, is you'll hire someone to try and find evidence of where an aquitard might exist so that you can drill a much shallower, more economically viable well into that perched water table instead of going all the way down to the main water table. Those are great. You find those? That's gold. Yeah.
There's also mountain water as well, right? It can be running water, right?
Oh yeah, mountains have running water all the time. But remember, we're talking about water, groundwater right now. And groundwater is going to continue seeping down through the rock until it reaches the water table, unless it's prevented from doing so in a situation like that, right? So how do we reach this water? We drill for it, okay? We stick our little straws down there and suck it right up. Now, most of the time, when we drill into it, we have to bring it up artificially. It is under some pressure, okay? That rock that water is sitting in is under confining stress, right? Confining pressure. Y'all remember that from metamorphic rocks? That confining pressure is providing it enough pressure that if it's given the opportunity, it will come out of the rock. That's what we call a spring, where it appears that water is just coming out of the rock. It's not actually, this is where that misconception that groundwater is like underground springs and rivers and stuff. Because you see this, where it's not coming from anywhere up there. It's not flowing down this hill. It's literally coming out of the rock. This is what happens when a perched water table, this guy right here, one end of it is exposed at the surface, like over here. And the confining pressure of all this rock on that water is squeezing it out of the rock where it is exposed at the surface. Lower pressure. High pressure moves into low pressure. It's true for weather. It's true for rocks, right? So you've got these springs, which is water being squeezed out of the pore space in your rock, and it looks like that. That pressure is not usually enough to force the water to come up our drill straws, okay, up our wells. We usually have to force it up. So we'll drill a well down into our water table, and then we'll have to install what's called a pump, okay? There are different kinds of pumps. Have any of you ever seen those old style hand pumps like this, where you crank it and water comes out? How does that happen? By pulling it up, you're creating suction in the well tube. And by pushing it down, you're pushing the water that got pulled up into the tube out. That's the hand pump. There are mechanical pumps, there are electric pumps that essentially perform the same function. So what you have to do to get water out is put energy in, basically. It has some cost associated with it, be that hand energy, like the energy of yourself, or gasoline or electricity. There is some required energy to bring that water out of the ground. Well, sometimes, if you're lucky, you might be able to find a body of groundwater that is under so much pressure, you don't need a pump. And we call these artesian aquifers. Basically, how these form are, instead of having nice flat layers, one on top of another, you have some sort of uplift in one direction, okay? Basically what you need is to have your layers not be perfectly flat. One end of your layers needs to be exposed at the surface. And then if they are the right types of rock, like say, here's, come on, red pen, don't fail me. Okay, there we go. Okay, let's say that this layer in the middle is our sandstone, and it is tapped on the top and bottom by layers of shale. Remember, shale being made out of clay, it's not going to let the water through it. And so any water that seeps into that sandstone from where it's exposed up here, that water is going to seep into the sandstone. It's not going to be able to move up or down. And so as more and more water gets pushed into it, you're probably going to build some sort of lake on top of it when this layer of sandstone gets filled up. All of the water down here is under an incredible amount of pressure from up there. It wants to be at the level of this lake because as far as it's concerned, that's the water table. Yeah?
The shale, is it above or below?
Both. It's above and below the sandstone. If it weren't above, that water would simply seep out up here, right? If it weren't below, then it's sandwiching it. Yep. Okay. It's sandwiched by shale. And so you have a bunch of water that is under a lot of pressure because it can't go anywhere, and it wants to be up here at the level of where this sandstone bed is exposed. Because that's its natural water table, and it can't reach it. And so we poke our wells down there, that water shoots up under its own pressure. Those are great. They require no energy input to get water out. The more artesian aquifers you can tap into, the better it is as far as the energy requirement is concerned, right? Artesian aquifers are awesome. We love it when we find those. Okay? Now, we have learned from this and replicated it using something that you see every day, but you have not known what its function is. Water tanks. The city water towers. There is a well underneath the water table that's tapped, or underneath that tank that's tapped into the groundwater. That water is pumped up here, and it fills this tank. Then there's another pipe that leaves the tank and goes to each of our houses and businesses. As far as the water in this second pipe is concerned, this is the water table, just like in the artesian aquifer. This being the water table, that water is under a lot of pressure to try and get back up there. And so when it comes into our houses, it comes out of our sinks and our showers and our baths and our garden hoses at pressure. There is no pump forcing it to do that. It's all the water tower and the fact that its perceived water table is way up here. The higher this is, the more pressure you got. Does that make sense? Isn't that cool? Yeah. Y'all never knew what those were for, did you? You thought they just held water. Or maybe you thought they were empty and useless.
Wait, so if the pipes like go to every house, how do they know what to charge us for water?
Because there's a meter. There's a meter of on everyone's house that measures water input, just like electrical output or input and gas input. All your utilities are measured by meters. Have you never walked back there and seen your meter? It's a gray box with a bunch of dials on it. They look like dials, and if you watch, you'll see them slowly tick up. You leave your garden hose on, and you'll see it tick up faster. Yeah, they're outside on the side of your house. Or if you're in an apartment complex, usually they will all be in one big shed with each meter like labeled by which apartment it belongs to.
We used to find a leak in our house once. We didn't know where if our house was like leaking water.
Mm-hmm.
So they told us to shut off all our taps.
Yep.
Go back there and watch where the flower needs to stay.
Yep, exactly. That's how you figure out if you've got a leak. Is it cheaper to have a water well than what? That depends. So city water sourced like this, the city can charge you based upon basically the rate that they consider that water is worth and the amount of effort that goes into getting it, right? We have a pretty poor quality of city water here, right? And a lot of places do as well. Some places have fantastic city water. They require minimal filtration or softening. The water we've got here is a little rough. If you wanted your own well, first of all, you'd have to pay for that well. You didn't have to pay for the city well. You just have to pay for the opportunity of using the water. After you pay for that well, you've got all the water you want. So as to whether or not your own well is better than using city water, that depends upon how dependent you want to be on city utilities and how much money you've got, right? It's kind of the same thing with installing solar panels on your house. I don't want to be dependent on city power, so I put solar panels on my house, but that's a $30,000, venture there. So I can pay $200 to $300 to the city every month in air conditioning costs because we live in Odessa, Texas. Or I can pay $30,000 right now or get a loan for $30,000 and pay that off. That's actually what I did. A year and a half ago, I got solar panels on my house. So I pay $109 for using my solar panels every month to pay off that loan that I got for it. And most of my power most of the power I generate, I use. Part of the end of it goes back to the city. So I usually only have to pay a few bucks in electrical to the city anymore. Whereas before I was paying $400 during the summer every month in air conditioning costs, right? So it made sense. In a place like this, solar panels make total sense. You go to Seattle, solar panels make no sense. They get 40 days of sun a year. So it's really dependent on what you want out of it, how much you can afford to put into it, and where you are, right? That answer your question? All right, great. Okay, now, you guys ever heard the terms renewable resource or non-renewable resource? Name some renewable resources for me. Huh? Wind energy, great. Huh? Solar, okay. Name some non-renewable resources. Petroleum, natural gas, coal. Okay, this is perfect. This is the point I want to make. It all comes down to perspective. As far as you and I are concerned, fossil fuels are non-renewable. It takes millions of years to make fossil fuels. As far as the Earth is concerned, it's perfectly renewable. If humanity just up and disappeared right now, there would be fossil fuels to the amount that there were before we started using it within 50, 60 million years. Maybe not that much, maybe 100 million years. Okay. It is totally renewable because things are living, dying, being preserved, and turned into hydrocarbons right now as we speak. Just extremely slowly. So we call those non-renewable resources because they are simply non-renewable to the perspective of that we wouldn't be able to use them. That's why we call them non-renewable. Not because they aren't, but because we won't be able to use them at the rate they are renewed.
Could we hypothetically synthetically produce oil?
Synthetic oil does exist, yeah. The only problem is the inputs you need to make it and making that cheaper, right? We can definitely make synthetic oil. You can make hydrocarbons without even needing life at all. There just needs to be the right situation. Making synthetic fuels cheaper is the trick, right? Right now, it's still cheaper to get the naturally occurring kind. So, the same thing is true for groundwater. The aquifer that you and I use right now to get our water, it's called the High Plains Aquifer, renews at about 1,700 cubic feet per, I think, what is it, like per day or something like that. 1,700 cubic feet is renewed, is pushed into that aquifer. However, we are consuming about 3,500 cubic feet. We are literally using water at twice the rate that it is renewed. Therefore, as far as you and I are concerned, it is a non-renewable resource because it is going to run out. Okay? And this is a big problem. This High Plains Aquifer, which, we're down here, right? But it goes all the way up here into South Dakota. That aquifer is used for a lot of agriculture. It's used to grow crops. It's used for herd cattle. It's used for a lot of things. It's used by cities. It's used for utilities. It's used for a lot. To the point where over the centuries now that we've been drawing from it, it is being depleted way too fast. Where you see in red, the water table has dropped more than 150 feet. Where we are down here, there's white, there's some yellow, some brown. It's dropped 25 to 50 feet. What happens if the water table drops below your well? Your well runs dry. It's already happening here. The church I go to over on John Ben Shepherd Parkway, we have 2 wells over there. Both of them have been dry for about 10 years now because the water table dropped below where they were drilled to. Every year that passes, more and more wells run dry here. And when that happens, you have 2 options. You can switch to city water, which is what most people choose to do, or pay through the nose for another well. Most people opt for city water, but what happens when the city wells run dry? Either there's a massive amount of money that the community needs to drill new wells, or you bring water in from somewhere else. There are towns in the West out here who literally cannot get water anymore, and they have to bring water in from other places to survive. Yeah.
Not to mention that also, like, a lot of companies come exploit, like naturally occurring water in this case. So, like, for example, like bottled water companies also have been known to exploit local, like, wells and springs.
Water rights are a major issue in our society. There are companies that totally bogart surface water so that they can sell it at the rates they want to. That does happen. It's essentially price gouging. And I will say this is not local to us. This is not unique to us. Africa is having major droughts because a lot of their groundwater aquifers are being run dry. So is India, right? So is Mexico. So are some other countries in Central America. There are lots of places that are having problems with groundwater. And remember, groundwater represents the majority of the non-frozen fresh water we have. And it's getting harder and harder to get to. So I'm going to give you all a little tip. If you haven't chosen a career, the next few decades are going to be extremely lucrative for hydrogeologists. I would venture to say Given the choice between full gas tank and water for a week, most people would pay through the nose for water. And I see that as the place where we are heading. As water gets harder and harder to come by and our population grows more and more, people who can find and explain how to utilize water in the ground are going to become extremely valuable. So I would recommend, if you have not chosen a career, considering maybe that one. There's going to be a lot in store for them. Yeah.
Eventually, in the far future, can we also get water from space as well?
Water from space. Okay, let's talk about that for a minute. Here's our tangent, right? It was about time we had one. James Cameron is very fond of talking about, for those of you who don't know, James Cameron is a movie director, okay? He directed the Titanic movie. He directed Avatar. He's directed a lot of good movies, okay? He's been involved in some of the Alien movies, the Alien franchise. If any of you guys have seen those, they're classics. They're great, with the exception of a few stinkers. He has a lot of money. And he's been very upfront with his plans to fund essentially space mining. Come on, camera. Stay with me here. It does not want to. Come on, camera. Look at me. I'm going to check and see what's up. Hello.
Sorry to interrupt your class.
No worries. What's going on?
See a few of your students.
Sure.
So Anthony Villalobos, you can see me. Sally Loba. Shanice Williams.
There we go.
Andy Soto. Alice. You can see me, please. Yeah. We'll be right back.
All right. No worries.
Sorry to interrupt.
Okay. Oh no, my camera followed Anthony. You keep following him instead of me, and I'm gonna start getting offended. Okay, where was I? Oh, space mining. He is dead set on space mining, which essentially means finding an asteroid that is rich in a resource you want, pulling it into Earth orbit, putting it in a stable orbit, and then sending astronaut miners up there over the course of however many years it takes to mine those materials. Now, this is a fantastic idea. I love this idea. There are entire asteroids made mostly out of metal and ice. The two things we need most right now. We can stop strip mining our planet. We can stop, pulling groundwater out. And we can start using metal and and ice from space. Thank you, Anthony. I appreciate that. Almost hide from the camera. Okay. Now, this is great in concept because it would reduce the stress on the resources in our system, right? And we would be able to utilize resources that otherwise will not be used that are just hanging out in space. What's the problem with this idea? How do we get them here? These are objects often moving at thousands of miles per hour. And if you want to talk about how you change their trajectories, it requires an incredible amount of energy. Even just a slight nudge would require a lot of energy. And you have to make sure that however you move them doesn't break them up. There are several types of asteroids, one of which is called a rubble pile, which is basically a bunch of rocks that have come together because their local gravity is kind of holding them in a loose group. You nudge that, and they'll probably break apart from each other. You need a solid chunk of ice or a solid chunk of metal. That's a lot of mass. You need enough energy to move that mass. You need your math to be perfect so that it ends up in Earth's orbit and doesn't hit the moon. You want to make sure that this object is not large enough that if you messed up or the intern who ran the calculations messed up, you don't accidentally send a giant metal asteroid hurtling into Paris, right? There are a lot of things that go into this. And so while it's a fantastic idea, we are a very long ways from being able to mine an asteroid. Yeah.
It's like a question from the water table, is
The water table? We will talk about water table quality here in another slide or two. No, that's great. Actually, it's this slide. It's the last point on this slide. I'll get to that, okay? No, it's perfect. I'm glad you're thinking about it. I had one more point to make. For about a year now, I've been in communication. I actually met her randomly at the airport. An engineer who works for Collins Aerospace. Okay, Collins Aerospace is the company that NASA uses to make their spacesuits. And so, like, we literally ran into each other while we were waiting in line at California Pizza Kitchen in the Denver airport. Okay, she was on her way home from Greenland, where they had been testing the new spacesuit designs. Okay, and we just kind of fell into conversation, and we ended up talking about her work. And now we communicate back and forth with each other about her projects. The project that they're working on right now, which NASA has not officially announced, but probably will in the next couple of years, is that they are planning the next mission to the moon to take place in the next decade, where they will set up a mining colony up there with several dozen people who their job is to establish a facility that can automate. It will be mostly automated, but it will essentially mine resources off of the moon to bring back to Earth. Why is that a good idea? No one's using the moon. No one can live on the moon. No one ever will live on the moon outside of maybe this mining base. The moon has great sources of metal. Remember, it's essentially early Earth mafic rock. It's rich in metals that we desperately need. And at the bottom of most of the craters on the moon that are never exposed to the sun is a large amount of ice. We can mine both ice and metal off of the moon. Why haven't we thought about this before? Well, we have, but we've had a long history of presidential administrations who are not interested in going back to the moon. Yeah. We couldn't take apart the moon if we tried, brother. I'm not talking about taking nearly enough material off the moon to make a difference. We would have to mine the moon for 1 million years before we took enough mass off to make a difference as far as its orbit is concerned, right? The moon is massive. It's not this tiny thing. It's about 1/8 the size of Earth. It looks small because of how far away it is, right? It's huge. Okay, so it's perfectly fine. If we can find some way to mine the moon, this removes a lot of the problems I was talking about with mining an asteroid. First of all, there's some gravity there already. We wouldn't have to fight gravity to make it work, right? Second of all, it's already in a stable orbit. It's not going to go crash into Paris if an intern messes up a calculation, right? There's a lot of the factors that are removed by mining the moon instead of an asteroid. And so I am super excited about that plan, right?
The only problem is that it's also, like, the path to get there will also be a lot dangerous for many people. So there's also, like mining on Earth, there will be, like, unfortunately, a loss of life.
It's inevitable that there will be, right? If mining on Earth is dangerous, mining on the moon will be even more so, which is why they're trying to make as much of the process automated as possible. Right? That way you just have a few people up there, maybe a couple dozen at a time on shifts, right? Maybe it's a year on the moon and a year back on Earth or something like that, right? Where basically all they have to do is maintain the equipment. That's the plan. Right now, the problem, well, I don't know if I should talk about that because this is going on YouTube and I probably shouldn't talk about too much of our conversations. Anyways,
Those are NASA secrets. They're gonna find you.
I know. They would find me.
Actually, I don't think of one issue.
Yeah.
So we're supposed to be getting metals off the moon, right?
Mm-hmm.
The moon's been microwaving in like cosmic radiation for a long time. Wouldn't that be an issue?
Yeah, the radiation that hits the moon is a big problem. That's why the outer surface of all spacesuits are radiation protected.
You know, like the stuff we bring back. Wouldn't that be a little bit-
Oh, will it be irradiated?
Yeah.
Yeah, but there are ways we can take care of that, right? And it's not going to be crazy amounts of irradiated, right? When I worked in the oil field in North Dakota, we had a room set aside for radioactive materials that came out of the ground. When my job was installing and taking out basically lift systems, and the lift systems that were old had been in the ground for decades. And oftentimes they had been sitting in radioactive layers of shale, rich in thorium, potassium, and uranium. Bring them out, run a Geiger counter over it, right? It's hot. We would stick it in a room, leave it in there for 6 months, and by then it probably would have enough half-lives would have passed that it's not as bad anymore.
What are half-lives again?
A half-life is the amount of time it takes for half of a radioactive isotope to decay into a stable daughter isotope. So if I have a kilogram of radioactive uranium, after one half-life, I will have half a kilogram of radioactive uranium.
So it like varies depending on the reactivity.
Each unstable isotope has its own unique half-life. Okay? So uranium-235 has one, thorium has one. There are unstable isotopes of potassium, each of which has their own. After each half-life, half of it is gone. So after 2 half-lives, I have 25% of that kilogram. After 3 half-lives, I have 1/8. Right?
Is it like a calculus question?
It kind of is. And this is actually, for those of you who maybe don't know this, this is where radiometric dating comes from. Because we know how long the half-lives for each radioactive isotope are, I can look at the ratio of unstable isotope to stable daughter isotope and see how many half-lives have passed, and that tells me how old that object is. That's how radiometric dating works. No, if you divide something, how many times can you divide 1 in half before there is 0? Infinite. That's why we use half-lives for dating. Yep. Yeah.
Also, like, I don't know if he's president. Also, Mars is also a good place for mine because there's also a lot of water on Mars, the poles.
There's a lot of water and resources on Mars. Mars is a much bigger problem, though. Why? Because it's a lot further away. When it takes several minutes for the speed of light, at the speed of light, it takes several minutes to go from Mars to Earth. And so if something goes wrong on Mars, Earth base wouldn't find out about it for a couple minutes, and there's nothing they could do about it anyway. On the moon, we'll find out about it in a few seconds, right? And hopefully have enough resources on hand that they could launch some sort of rescue mission within a day or two. On Mars, you'd be on your own for at least 6 months. It's a much more complicated proposition to mine on Mars. And at that point, you have to ask yourself, is the quantity of materials going from Mars to Earth really worth the energy, time, and man hours, right? That goes into going there to mine. The moon is a much more viable option. So that's where we're at. I'm going to bring us back to center from this tangent. It's been a fun tangent, but now we're coming back. Okay, so as we are pulling water out of the ground, it is emptying that pore space, right? That pore space, once occupied by a fluid, is now empty. What's going to happen to that rock? Good. You did this. Tell me, use words.
Would it collapse?
Yeah, it's going to compact even more. The pore space isn't being occupied. Good job. Okay. That's exactly it. Now, what does that do? As you get compaction underground, you're going to make holes on the surface. Sinkholes. Okay. That's one very common reason why sinkholes form. Ground subsidence, thanks to the withdrawal of fluids that has created empty space underground. Either that or there is a cave network under there that has grown large enough that the top surface rock can no longer support itself above it and it falls in. It's very common in Florida. Okay. Now, Sam asked a question earlier about, is groundwater pure? Can you drink it? The answer is yes. The cleanest water I have ever tasted in my life. And I want to give you all some context for this. What I'm drinking today, this is water. You probably will never see me drinking a soda. I very rarely drink juices. Water is my favorite beverage. I love water more than anything else. Huh?
Even when you eat?
Even when I what?
Eat.
Eat? Yes. I only drink water when I eat. Drinking anything else feels gross.
I don't know about that. You don't drink coffee?
No. Although I don't drink coffee or tea or any of those things. So. Huh? That's why my skin is so white. It has nothing at all to do with my Russian and German ancestry. Oh, okay. I definitely heard white. Like, that's probably not it, but okay. That's why my skin is so nice. Thank you. I appreciate that. That's a lovely compliment. No one's ever told me my skin is nice before. You okay?
Did you hear the
Like static? Is that what that was? Oh, okay. Anyways, my point is I love water. I am a connoisseur of water. and the cleanest, most delicious water I have ever tasted in my life was when I was swimming in a lake in Iceland with water that spent 10,000 years filtering through layers of basalt before coming out. It was the most pure water I've ever tasted in my life. Like literally, I'm just like, I'm in this lake and I submerge myself. I'm just like, I'm drinking this water, right? You open your eyes and I can see 1,000 feet away because of how clean this water is. Legit. What? It was freezing cold. It was in Iceland. Okay? It had a taste. Yeah. When I say clean water, I don't mean there's only water in it, right? Clean water also has like the right quantity of essential minerals for you, right?
So it's right about acidity, right?
Mm-hmm. Perfect acidity, perfect quantity of minerals, nothing nasty in it whatsoever, because it's been 10,000 years filtering from glaciers through basalt until it ended up in that lake. Okay? Fantastic. That's what groundwater is supposed to be, okay? Not all of it is just as clean as that. Water that has filtered through various types of sedimentary rock has usually picked something else up along the way, right? And so, like here, our groundwater is a very, very nasty groundwater because there is sedimentary rocks that contain some nasty things, okay? However, we can accidentally artificially pollute groundwater as well. When I was living in Hawaii, there was a big news story that broke about how some kids in a neighborhood started getting sick. And they couldn't figure out why they were getting sick. And it was just the kids in this particular neighborhood. And so they were like, well, let's see if there's anything in the water. And so they tested the water and they found that there were some toxins in the water that were responsible. So to try and figure out where the toxins were coming from, they sampled from every well in the area. And using the wells that had the highest concentrations, they kind of searched the neighborhood around the wells that had the highest concentrations of these toxins. And they found that the local laundromat for decades had been dumping their waste chemicals in their backyard. You're supposed to take those to a special place and dump them in a special receptacle, but that costs a fee. And to save some money every month, they just dumped them in their backyard. Well, after decades, it percolated down into the water table. And now it was making kids sick.
Why only kids?
Because kids are most vulnerable to most diseases or toxins. Adults tend to have a much hardier immune system that can take things like that. There were some adults that had some effects as well, but the kids were getting really badly sick. So yeah, those people went to jail. Rightly so. They contaminated an entire water table. And it took decades for it to get contaminated and decades for it to get clean again. Right? This is a long-term impact. It takes a long time for those things to work their way out of the system.
How much money did that cost? Like in damages?
Probably a lot. I don't remember that much about it. Okay? So, this is serious. This groundwater, we rely on it for a lot of stuff, and we have to take care of it. Some other things we can learn from or use the water table for. When you have water in the water table or in the groundwater system that is in contact or near volcanic heat, that makes what we call a geyser or a hot spring. It can make both. And if you've ever been to a hot spring, that water is hot because it's being fed from a volcanic heat source. A geyser. You guys ever heard of Old Faithful at Yellowstone? Actually not being as faithful lately, right? It's experienced some variation in its consistency, but it's a massive geyser that periodically will shoot steam and water up into the sky. Why? Because the water table is getting heated up from the magma, which is actually only a few kilometers below the surface at Yellowstone, right? And it's being heated and turned to steam and blasting out the surface. Falls back down, seeps back in, fills back up from the groundwater around it, and then blasts back out again consistently. You could. It would be nasty because it's probably pretty sulfurous. Yeah, I wouldn't.
You are a water connoisseur.
Yeah. I told you, right? However, we can use this fact by taking water, which naturally is near a source of heat, And then bringing up to the surface, it will turn to steam. At lower pressures, hot water that is at the boiling point will turn to steam, right? And so we use that steam to turn turbines. This is called geothermal energy. You heard that term before? Geothermal energy is using water, using the heat from nearby volcanic sources to turn water into steam to turn a turbine, which generates electricity. There's no fuel involved here, just steam that occurs naturally as a product of volcanic heat. This is a picture I took of a massive geothermal heat facility in Iceland. Because they have so many nearby volcanic sources, they use this a lot. A lot of their capital is powered through geothermal energy. If you walk into any of their larger like government buildings in the capital, Reykjavik, there's this nice, toasty, comfy, warm heat in that building. And you're like, ooh, this is nice, but there's no vents. Where's this heat coming from? They are piping volcanic water through the walls to heat their buildings. There are so many ways you can use this in a much more efficient, reliable, sustainable system than the ways that we use, right? The only problem is there isn't a source of volcanic heat nearby everywhere, so we can't all do it. Yeah. Yes, that's the capital, Reykjavik. That's Icelandic. Yeah, they have lots of really fun words. Actually, if I could pick one language in the world to learn, it would be Icelandic. I spent about a year learning some of it. That was about 7 years ago, so I don't remember much. But I was able to communicate a little bit in Iceland, and they actually complimented me on how well I was saying the words. I was like, oh, thank you. So I'd love to go back to learn it at some point. But yeah, they have lots of fun names. The volcano that erupted back in 2010, Eyjafjallajökull, really fun word, right? They have really cool language. And there's the added bonus that only about 300,000 people in the world can speak that language. So, okay, 300,000.
Oh,
Yeah, the native population on Iceland is about 150,000, I believe. And then you got to count all the people who have, left Iceland to live everywhere else, but still speak the language. It's such an obscure language that they don't actually have like Babbel and all of those other language learning websites and apps. They don't actually have Icelandic as an option. So you have to go to like an Icelandic company for the materials to learn about their language. Okay. All right. These are what sinkholes look like. Oftentimes, they'll appear in the middle of nowhere where you don't really need to worry about anywhere but your sheep herd, right? Those are all sheep. Okay, those little white dots, those are sheep. And they couldn't care less. But sometimes they occur in the worst place possible, right? And really, the only way to know that they could occur at all is to do an in-depth, pardon the pun, geologic analysis of the area before you even build anything on it. A lot of people don't bother paying for that. Okay, so you got to know a little bit about where you are and the tendencies of that area. For example, if you are moving to Florida, you should probably expect that sinkholes are a threat. They happen there all the time. You move to Idaho, you probably don't have to worry about it, right? So knowing the general geology of your area can be very, very valuable for you, your safety of your family, and the sanctity of your home. Okay, so these are relevant things that you learn. Yeah, so a sinkhole can form one of two ways. Either a cave has formed underground over the course of millions of years, you just didn't know it was there, right? And it's grown to the point where the top layer of rock above it, between the surface and the top of your cave, is no longer supported. This happens a lot if you build something on top of that. Yeah, you put a building on top of your cave you don't know is there, it's going to collapse in because of the extra weight, right? Where before it was stable, now it is not. Another way that these form is through subsidence, okay? So essentially, you have pulled so much water or oil or whatever fluid was down there out of the pore space, out of so much rock, that your rock compresses even more into that now available pore space. And even if it's only even if each foot of rock only compresses a millimeter, if I have 100 feet of rock that's been compressing, that's 100 millimeters, and that's going to be pretty substantial subsidence on the surface. And that can do things like crack foundations or even break houses entirely, depending on the size and the construction material. Yeah. Any questions about groundwater while I move on to glaciers? I didn't make any changes. You're crazy.
Have you had spring water in Fort Davis?
Have I tasted it?
Yeah.
No, I've only been to Fort Davis once, and it was during a drought, so all the pumps were off. I camped there.
Okay. 'Cause I used to start using it there. And the groundwater over there was Ozarka quality.
It's what?
It was Ozarka, like, you know, that Ozarka bottle brand?
Yeah.
That's actually.
Oh, yummy. Yeah.
I am going to Big Bend that weekend, so it's great. So
Nice.
I love the Big Bend. I get you pictures from last time I went. This during Christmas break actually.
Yeah.
I want to try to catch because at that point blackbears come out of hibernation, so I want to get pictures of them. And then after the Rio Grande Valley, I want to see if I can see a thing called or a bird called a black hawk, which are usually found throughout South America and Central America, but do come up the most southern tip of Texas, Big Bend area.
Interesting. Have fun with that. All right, let's move on to glaciers. You ready? Okay. Let's talk first about how amazing water is. I know I already spoke about how much I love water, but water has some pretty amazing physical properties. Okay, we're going to talk about some of those today. First of all, water has cohesion. You guys know what that word means? It sticks together. Water likes water. If I have a pane of glass, say a windshield, and I drop some water like a raindrop on it, what does the water do? It stays together. You get a drop. You get a bubble of water on your pane of glass. If I did the same thing with a little drop of oil, what does my oil do? It spreads out. It spreads thin. Oil has much lower cohesion than water does. Water molecules love sticking together with water molecules. We have bodies of water all over the place. Water stays together in streams and in rivers. It stays together in lakes, right? Water stays with water. That's the first amazing property, cohesion. The second one is how it absorbs heat. Okay. All right, how it absorbs heat. Water absorbs heat at a slower rate than the land does. The ocean will absorb heat at a slower rate than the land does, but it will also retain it better. Okay, so this is relevant in a major way to human civilization. Way back when, a lot of early civilizations were built up on coastlines around fishing industries. Okay, so you're in your fishing village, and the sun starts to rise. Okay, as the sun is rising, it is warming both the ocean and the land. However, the land warms up faster. Therefore, you get warmer air over the land than you do over the ocean. Hot air moves into zones of cold air, right? High pressure into low pressure, warm into cold. That's how the weather works. That's why we get weather at all, right? And so there is a breeze going from land out to sea as a consequence. This is the breeze that our fishermen ride out to sea to do their fishing for the day on. Now, as the evening is coming and the sun is falling down low, the land is cooling off faster than the ocean does. The ocean is spent all day warming, just like the land does, but it holds the heat better. And so your land is cooling off faster. Therefore, we now have a breeze that goes from ocean to land. And they ride that back into their village. Out to work in the morning with the sun, back home with the setting of the sun, following the breezes. This is actually where the first concept of a workday came from. Our 9 to 5 is a derivative of this phenomenon. Okay? That's where it came from. That's where it started. So, why does this happen? Because of the fact of how water absorbs energy. Slow in, slow out. Okay? Something else. If I were to freeze water, it becomes a substance we know of as ice. Ice floats on water, correct? Why?
It's expanded.
Okay, so our quantity of water has expanded through becoming a solid, which, first of all, weird. Most things contract. What does this do that causes it to float on water?
It's the same mass, taking more volume means it's less dense.
Same mass is constant. Change in volume, to increase the volume, our density has changed. Remember, density is a measure of mass per unit volume. Therefore, if our mass is constant and density and volume increases, our density decreases, making it more buoyant. Should I throw something at him? I should get a marshmallow gun. That's what my instructors did. Right? I get it. You're tired. All right. So this is cool. We have the same chemical signature, just in different states, and a change in density causes this to be buoyant on top of the liquid version. These are three amazing properties that water has. I just want you all to have an appreciation for water real quick. And also something you're going to notice under the rest of our lecture today is how even as a solid, ice behaves in many of the same ways that water does. You'll see that today. So, ice is a mineral. Y'all remember the conversation we had? I think this was day 1 or day 2 of our class. Why is it a mineral? What's our definition of a mineral?
Something with the uniform crystallized structure and also it can be represented by a chemical formula.
Let's start at the beginning. It is any naturally occurring, inorganic, solid
The uniform crystallized
that has a orderly crystalline structure and can be represented by a chemical formula. Ice is all those things. Ergo, it is a mineral, according to geologists.
It has a very low volume.
Huh? Are you reading or are you asking a question? This is why glaciers fall under geology, is because glaciers are made out of ice and ice is a mineral.
It just has a very low melting point.
Does that make sense? Okay, yeah, and you're right. It has a melting point just like minerals, all other minerals do. Granted, a much lower melting point, but still, it has all the same properties that minerals do. Okay? As far as we're concerned, it belongs to us. Haha. Right? Now, glaciers move. How weird is that, first of all? Glaciers move. Have any of you ever seen a glacier move? Yeah, I haven't seen one move either. But they do, and we know they do. And we'll talk about evidence for that here in a minute. The way that glaciers move is through something that we call plastic flow. Okay? Plastic flow. They behave plastically. What is plastic? Someone tell me what plastic is.
Like being able to be, like, I guess, changed or adapted, I guess, or like altered.
When I say plastic, what do y'all think of?
I was going to say something pliable.
Plasticity, I guess.
You think of this. You think of this. You think of this. Think of this. You think of this. You think of this. How many things are around me made out of plastic? So many things. So many things are made out of plastic. But my buttons are made out of plastic. Are they all made out of the same stuff? No. They all have different chemistries, right? This plastic is nothing like this plastic, is nothing like the plastic that makes my desk. And yet we call them all plastic. These are all polymers with different types of chemistries, but we call them plastics. Why? I want to change your perspective on the word plastic today. Plastic, where before you may have described something as plastic, using that word as a subject, this plastic, I want you to think of the word plastic instead as an adjective. Hi, what's up?
Well, we went to see snakes, but I see you have a class.
Uh-huh.
And I don't know where you want to put this, but I have a slip on in.
What? Is this for me?
Yes.
Thank you.
It's late, but
Thank you. That's very sweet.
You're welcome.
Appreciate that.
Have a good one.
You too. Put that right there. That was cute. Yeah. Okay.
I want to like swat like a cat.
Yeah, you want to treat it like a cat toy, don't you? Refrain. Refrain, huh? Yeah, I know it was for the snake. It's not for me. Oh, you want me to put it on the snake?
I was gonna fly away.
He's not gonna float. You kidding me right now? Yeah. Here, buddy.
It says gonna be poking out.
There we go. I'm sure this doesn't look goofy at all, does it? What? Did it fall off?
No, it gets stuck on the projector.
On the projector?
Well, it bumps it.
Oh, that's fine. I don't care. All right, you got your Valentine's balloon, buddy. You happy? Okay. I feel like that kid in Up,
With the wooden bird.
but I don't have a bird. I have a snake. Yeah. Okay. Where was I? Okay, plastic. Plastic not as a subject, plastic as an adjective. Plastic describes the thing. It is not the thing. Plastic is a word that describes how you can manipulate a thing. When I describe something as plastic, that means that it is a substance that can be molded. It can be shaped. I can use pressure or heat to change it. Okay? So I use various polymers to make any object that I really want, and I call it plastic. Glaciers move through plastic flow. Does that mean more to you now? Does that have a little bit more context what I mean? Someone take a stab in the dark. What do you think I mean when I say that glaciers move through plastic flow?
It could be melted, heated, or molded, and it can vary in shape and shape and appearance, but also in how it, like, for example, could be more I guess compact, but it could also be more flowing into here. So it could do again through melting processes and freezing processes.
Let's assume that melting doesn't play a factor here.
We can mold around like solid objects that are around them.
Okay, it can change its shape based upon what though, do you think?
Glacier can also be weathered and eroded as well.
They can be, yeah. What could cause my glacier to change its shape? Huh? A mountain? Usually they form on a mountain and go down the mountain, so they are changing their shape around the mountain or scraping off pieces of the mountain as they go, and we'll get to that. But what is the driving force behind the plasticity? Gravity is causing the downward movement. What's causing the plastic deformation?
She said melting, not
Mounting?
melting.
Oh, melting. Oh, no. We just talked about that, okay? Melting, that's not a factor here. Changing from solid to liquid, sure, yeah, it's changing its shape. It's changing things about it. That happens to everything. It is changing its shape based upon pressure. Pressure of what, you ask? I'll tell you in a minute.
Atmospheric pressure.
Not atmospheric pressure. We'll get back to that pressure in a minute, but it is changing its shape around things as it goes downhill. Anything that can't break up or scrape away, it changes its shape around. Okay? So, a glacier is a very thick mass of ice and often takes thousands to tens of thousands of years to form. Why? Where does ice come from? Water. Namely, what kind of water?
It could be either fresh, but also it could also be ocean water.
Have you ever heard of salt ice? No. You can only make ice out of fresh water. You can get glaciers from salty water, but none of the salt makes it into the ice, right? Snow, right? Most glaciers form through snow. Glaciers scrape up lots and lots and lots of material on their way slowly downhill. As they are deforming over the mountain, they are scraping lots of stuff off the mountain as they go. Okay? Should I take it off?
No.
No, absolutely not. Okay. Glaciers are really cool because they represent an intersection between the hydrologic cycle and the rock cycle. Why? They are water, therefore part of the hydrologic cycle, the solid part of it, and they are a mineral or a mass of minerals, right? What do we call a mass of minerals? A rock. A glacier is basically a rock, okay? It's a mass of minerals, okay? And so it is both part of the rock cycle and part of the hydrologic cycle. They're a little weird, okay? Now, 65% of all the world's fresh water is in Antarctica. You guys remember we had a whole conversation about Antarctica? There's a whole continent under there of untapped resources, of untapped potential, of untapped fossils. We've gotten a few fossils. The dinosaurs in Antarctica actually looked a little weird.
Cryolophosaurus is pretty interesting.
Cryolophosaurus is a weird looking thing. It had this weird crest, like I don't know, like it did its hair weird for prom or something. Okay. But there are lots of weird dinosaurs on Antarctica, and I'm sure there are tons more in the rock underneath of the ice that I would love to see, but probably never will in my lifetime. By the way, backing up a second, when we're talking about mining the moon, here's another big thing. When America sends people up there to go mine the moon, what are the other major countries like China and Russia going to say about that? Right? They're going to say, over our dead bodies, or we're going to get there and do it too. The moon will basically be the Wild West, right? As far as utilization of its resources and who sets up where.
Cold
Are
War
you
Part
showing
Two.
Cryolophosaurus, yeah.
World War II?
It's like Cold War Part Two.
Cold War Part 2? That would be a very
When
cold war up there.
Antarctica melts, and this is not a freaking.
Right. Well, and then this is the other thing. How do they know we're not setting up weapons facilities up there? How do we know they're not doing the same thing? There's a lot that goes into this debate. Okay, but that's melts. All right. So 65% of all the world's fresh water is in Antarctica. If all of that melted right now, sea levels would rise about 60 to 70 meters. This is what the U.S. would look like if that happened.
Louisiana just completely died.
Louisiana's gone. Florida's gone. Most of South North Carolina, most of our East Coast is actually gone. New York's underwater. The entire Mississippi embayment, all the way up to Memphis, Tennessee, is underwater. San Francisco's underwater. Look how big San Francisco Bay has become. Seattle is underwater. The Puget Sound is huge now, right? Our world would change a lot if that happened.
A very wetter world.
Yeah, right. 70% of the world's populations live on the coastlines. Just to give you some context. That would be a lot of displaced people, right? And like it or not, we are heading towards something like this. Will this be the end result? Will all of the glaciers on Antarctica melt? Highly unlikely. But there is going to be some sea level rise as climate continues to shift. And so there are going to be displaced populations of people. That is for certain. Okay. There are several different types of glaciers. A valley glacier is your kind of, you think of a glacier and this is what comes to your mind sort of deal, right? They are glaciers that reside in a valley, okay? The sort of U-shaped valley that they've scooped out of the side of the mountain. Typically, these will start as some stream or riverbed that the glacier moves into and kind of scrapes out a wider channel for itself. They can be quite long. This is the Hubbard Glacier in Alaska. It's a very long glacier. Just right here, let's see, there's 1 mile right there. That's like 8 miles of glacier you're looking at right here just in this picture. And it goes further up the mountain. Okay. Other types of glaciers. Ice sheets. There are only 2 ice sheets on Earth right now. An ice sheet is where you have a central source of ice forming that feeds, kind of spreading out radially from the central source, is pushing ice out from the central source, and the ice is kind of moving out over an area. So Greenland is an ice sheet. Antarctica is an ice sheet being fed from the center.
Yeah, I don't know. You always like looking up to this view.
Oh, no worries. Okay. An ice cap is essentially kind of like a small ice sheet. Okay. And there are more of these. There are several in Iceland. There are a couple in Canada. Basically, an ice cap is where you have the sort of central feeding out to multiple glaciers that spread out from that central point. But it usually only happens in a local mountain range, for example, where you have a collection of mountains versus over an extremely wide area like the ice sheets do. Okay. Then you've got an outlet glacier. An outlet glacier is essentially a glacier that kind of went rogue from an ice cap, started doing its own thing, and kind of like see out here would be the ice cap covering the top of the mountain range. And then this glacier is like, I'm going to go out here and do my own bit. That's an outlet glacier. And then a Piedmont glacier looks like this. This can be either from an outlet glacier or it can be from a valley glacier where it reaches the bottom of the hill, wherever it feeds out from, out of the mountain, out of its valley, and it spreads out like this. Does this look like anything to you guys? Does that look familiar in any way? It looks like an alluvial fan. Excellent. It does, doesn't it? This alluvial fan is being fed by what? A glacier, not a river or a stream. But notice how, just like how the water, when it reaches this flat area, spreads out, loses its energy, and drops all its sediment, this ice is doing the same thing. The ice and the water are behaving in exactly the same ways. Remember how I told you there would be examples of that today? Isn't that interesting? Even though it's a solid, it's still behaving in the same way. All right, let's make a shopping list. What do we need to make a glacier? Water in the form of, well, yes, it'll be fresh water in the form of ice. It's got to be ice, right? Yeah. You're not going to make a glacier. I'm not going to get a whole bunch of liquid water in place and make a glacier, right? It needs to be ice, okay? Where do we get ice? Snow. Where do we get snow? Cold temperatures, which form. Where do we get cold temperatures on Earth? High elevation or really far north or south, right? You all agree with this? Okay, the high elevation, let's talk about that because we get ice that forms on the equator. If you ever go to Hawaii, the big island of Hawaii, take a hike up their tallest volcano. I did when I was there. I had a snowball fight with my brothers. There's ice up there. There's snow in Hawaii. Why? Because it is high. It is tall. Temperature decreases the higher you gain in elevation. Why? Where are you going, buddy? Okay, why? Who wants to take a stab at why temperature decreases the higher you get in elevation? The atmosphere is cooling off. Huh? It doesn't have to do with getting further away from the core. That's a good guess, though. There is a change in pressure, not significant enough to impact what we're talking about.
Different wind conditions or weather, like different weather conditions.
You're further away from the Earth's surface that is absorbing the heat from the sun. Okay? So the further you get from the Earth's surface, the less reflected heat you are experiencing. It is spreading out, losing energy the further up you go. So, higher we are in altitude, the lower the temperature gets. There comes a point, there is an invisible line, you can't see it, but it exists up there, called the snow line, above which snow can remain year-round. Huh? No, permafrost can occur on the ground. That's where temperatures are cold enough year-round that not the whole soil layers melt, unthaw, or unfreeze, okay? So you get snow above your snow line. I'm just going to jump ahead here. This is Mount Kilimanjaro. Where is this picture? How do you know it's in Africa?
Giraffe and also just savannah.
Yeah, the giraffe is a pretty good indicator. This is in Tanzania. Mount Kilimanjaro is an extremely tall, extinct volcano. Well, maybe extinct. It's dormant at least. Okay. What do you see up there? Yeah, snow. Those are actually glaciers. Now, when I say Africa, do you typically think snow? No. And yet there it is. Why? Because it is above the snow line, where snow can remain year-round. Now, your snow line can fluctuate up or down, depending on things like season and global climate change. The hotter Earth gets in general, the higher up your snow line gets. The higher your snow line is, the less land mass is above the snow line, therefore the less glaciers you have, and more glaciers melt, which is what we are beginning to experience. Okay? So, snow falls in the form of some hexagonally shaped crystal. How many of you learned as a kid that two snowflakes ever look alike? I am so sorry to break your childhood, but that is not true. There are actually only about 26 shapes that snowflakes can make. They're all variations on hexagonal prisms, but there's only about 26 shapes that they take. So the likelihood that you would get two of the same shape when you're looking for them, very unlikely, which is probably where that myth started, but it is not true. There is no infinite number of shapes they can take. Okay? So you get the snow, and it falls down as drifts, okay, big piles, and it gets blown this way. You'll be okay. Snakes fall out of trees all the time. You'll be fine. It's not like he's going to break a leg. Okay, so you get drifts of snow, and they're blown this way, and they're blown that way, okay? Over time, because they are not melting, over time, they get the little edges broken off, and you go from these nice hexagonal crystals to kind of little nubs or little rounded balls of ice. We call that firn, F-I-R-N, firn, okay? And it is that firn that ultimately goes through the process of becoming glacier ice. How does this happen? As these piles of firn get deeper and deeper and deeper, they're going to start to compact and fuse together. Does that sound like anything to you? What kind of rocks? Sedimentary rocks. This is essentially the sedimentary process. Weathering, breaking down of sediments that ultimately get buried, compacted together, and make a thicker unit of ice. This is basically the sedimentary process. Yet another example why it is relevant to study in geology, right? And from there, that's where you have your glaciers. This can take a very long period of time. Not as long as it takes for rocks to form, mind you, but still centuries to millennia, okay? Very rarely, sometimes it can take decades. You can't make a big glacier in a matter of decades, though. You need a lot of ice to make a glacier. Okay, so how do they move? That plastic flow. That is the primary method of their movement. Now, we learned before that it is pressure that causes plastic flow, but we never discussed where that pressure comes from. That pressure comes from the mass of ice above the rest of the glacier. You need a certain amount of weight on your glacier to cause them to deform plastically at the bottom of the glacier. He lost the balloon, didn't he? That's fine. I'm fine with it hanging out right there. Yeah, he was probably trying to get rid of it. Okay. So you need a certain quantity, a certain mass of ice to induce plastic flow. How much ice? About 50 meters. Once you have 50 meters of ice, everything below those 50 meters has enough weight on top of it to deform plastically. So while I'm walking up here and I'm kicking around and I see rigid, hard, sharp, cold ice, 50 meters below me, that ice is slowly deforming plastically because of the pressure of all the ice I'm walking on. This is true if my glacier is 55 meters thick or 500 meters thick. Okay? Deformation occurs after that much ice is present, causing that pressure. That's the primary method of movement. There is another way that glaciers can move as well. This is called basal slip, and this is where slight melting comes into play. Okay? Now, because your glacier is typically colder than the rock that it sits on, there is normally a very thin layer of water at the very bottom of your glacier. And every now and then, especially if you're on a steep slope, your glacier will just kind of like, or parts of your glacier will kind of just slip over the rock because there's that thin water layer. That's called basal slip. That's another way that they move, but the primary method of movement by far is plastic flow. Deformation of your ice over your body of rock that it's on top of. Does anyone have questions about deformation, plastic deformation, anything like that? No? Okay. All right. Let's talk about everyone's favorite subject, budgets. Who doesn't love talking about a good budget? Who here lives on a budget? If you're not living on a budget now, wait until you have your own income, and then you better be living on a budget. You're going to be hurting fast, right? What is a budget? Yeah, it's about money. What is it about money specifically?
Saving it.
Yes, input and output. A good budget is where you have more money coming in than you have going out, right? That's how you and I think of budgets. Believe it or not, glaciers have budgets too, but they're not worried about money. They're not worried about anything. They aren't animate. But what do they care about? They don't care about anything. They're not animate. What is a glacial budget? What resource could glaciers possibly utilize in a budget? Snow. Bingo. Okay. So where you and I require more money in than goes out, if we have a healthy budget, they need more snow in than they have out. Okay. So where does the snow fall? Above the snow line. Above the snow line on our glacier is what we call the zone of accumulation. Where does that happen? Above the snow line. This is important. What happens there? Snow accumulates. That's where your ice is formed. That's how you are making material to feed your glacier. Where does it go? Downhill, below the snow line. Below the snow line is what we call the zone of wastage. What's happening down there to make us call it the zone of wastage? It's melting. It's breaking off. By the way, when a chunk of ice breaks off of a glacier, we call that calving. Just like when a cow gives birth. Okay, it's calving. Okay, so snow line is here, zone of accumulation, zone of wastage. There is the potential to lose mass down here and gain mass up there. When we are acquiring more ice above the snow line in the zone of accumulation than we are losing in the zone of wastage, we have what we call an advancing glacier. An advancing glacier, the front is moving forward downhill because it has a positive budget. It is getting more than it's losing. A retreating glacier, what do you imagine that means? It's melting relative to what? It's melting faster than it's gaining snow mass. Bingo. And when that happens, our glacier front is moving backwards. Now, I want to be very clear here. The glacier is not pulling itself back up, is it? That would defy physics, right? That mass of ice is not all of a sudden moving uphill. However, because it is melting faster than it's gaining mass, the front of it is continually retreating uphill. Does that make sense? Does that difference make sense to everyone?
So retreating
It's not pulling uphill. It's just melting faster than it can be renewed. And so the front is moving uphill.
retreating is melts.
It's melting faster right here than it is gaining mass up there. And so the front keeps going further and further uphill year after year. Okay. Everyone clear on that? Okay. Now, these are massive forces of erosion. Okay. I'm talking about trillions of tons of ice pulverizing everything in their path. Okay. So oftentimes they will break off chunks of rock and carry them with them. Glaciers are essentially a giant conveyor belt for sediment going downhill. Okay. So they pulverize rock, take all the material downhill, and that material gets deposited wherever that ice melted. Okay. So this giant boulder out here in the middle of this field, any Shrek fans? That's a nice boulder, right? Okay. Do I embarrass you guys? Okay, so that boulder out here it's not like anything else out here. It's the only one out here. It's probably made out of a totally different kind of rock too. Where did this come from? Well, there's a valley back there. What is the most likely scenario for why that rock is here? What took it? A glacier brought it. This is what we call a glacial erratic. A glacial erratic is a giant rock that has been plucked. That's the process. It's been plucked from one location and deposited somewhere totally different by a glacier. In the town I lived in Ohio, there was a state park. It's the state park where I lived nearby, okay? And next to the parking lot of the state park was a massive chunk of granite about the size of my house. I loved climbing on that thing. I'd sit on that thing, eat my lunch, whatever, right? Big chunk of granite. Here's the problem. There's no granite in Ohio. Where'd it come from? It hitchhiked on a glacier all the way from Canada down into Ohio. From the last ice age, when a glacier made it all the way down there. Okay? And that was a glacial erratic. Okay? Abrasion is when a glacier has melted far enough back up the valley that you can see the surface that it was on top of has kind of gotten scraped clean. You see these grooves? Those grooves form because along the bottom of that glacier, some rock got scraped between the glacier and then the rest of this rock. Literally between a rock and a hard place here, right? And it got scraped down into very, very fine powder, which we call rock flour. But in the process, it carved this groove into this bottom rock surface. And you do that enough and you get a whole bunch of them along that surface. That's called abrasion. And then obviously, as I mentioned, calving is what we call it when ice falls off in chunks off of your glacier. Okay. I need to do a hand demonstration. You want to hold it for a minute? Yep. Okay. Got some models here to show you for this next bit. Okay. Can you all see this? Yeah? All right, here we have a valley glacier and several side glaciers that are feeding into that one. Okay, so let's talk about some of the parts of this glacial system. Okay, starting with your valley. First of all, your valley is your central sort of depression that has been carved out by your glacier. Like I said earlier, it usually starts as a stream bed or a riverbed. And then once your glacier moves down into it, it carves it out into a much wider, usually U-shaped sort of valley. Okay. Then you've got a cirque. A cirque is the kind of side glaciers that you see feeding into the main one. Okay, let's say that's our main glacier right here. These side glaciers Those are called cirques. Okay? Think of them as tributaries, like how a tributary stream feeds into a larger one. Okay? Then you have arêtes, which are the sharp ridges between your cirques and your valley. Okay, those sharp ridges. And then a horn is where you have multiple arêtes that meet up. So that's a horn, and that's a horn, and that's a horn. Okay? Between these cirques and valleys.
When you jump for fjord when you're like melted, or is it?
Yes. Have any of you ever heard the term fjord before?
I've heard using the term fjordland as in New Zealand.
New Zealand has lots of fjords. Iceland, Greenland, Norway, Sweden, they all have lots of fjords. But what is a fjord? A fjord is when, during the last ice age, you had a lot of glaciers that made it all the way to the coastline, what was at that point the coastline. But then things started warming up. Remember, we have left the last ice age. Last ice age, the peak of the last ice age was 11,700 years ago. We've been warming up for almost 12,000 years.
It's not a little bit of an ice age, but it's like it's not as prominent as it was.
If we're getting technical, an ice age is when we have ice at both poles. And so yes, we are still in an ice age. What we left was a glacial maximum. As far as you're concerned, we can call it the ice age within the concept of this class. I'll get more specific if you all get in 1404. Please say 1404. It's lots of fun. Okay. However, what happens when all of the ice melts and goes into the ocean? What does the ocean do? It rises. Okay. So during an ice age or glacial maximum, we have low sea level because a lot of water is bound up in the glaciers. Between glacial maximums, when a lot of ice is melted, we have high sea levels. And so where during that last glacial maximum, there was your glaciers went to what was at that point the coastline. Now we are between those glacial cycles. A lot of water is back in the oceans. Our sea level has risen. So now let's say it's right here. And that's a fjord. A fjord is a drowned glacial valley. That is, the sea level has risen and filled in some portion of your glacial valley. Okay, that's a fjord. During World War II, the Nazis were very fond of building submarine bases in Norwegian fjords. And to this day, there are still several that have not been found. Fun fact. Because there are literally hundreds of them. And every time a US submarine would chase a Nazi submarine into the fjords, they'd lose them because the Nazis had it all mapped out and the Americans knew nothing about it. So they'd be able to escape and get to their secret bases. Okay. There has been so much fiction about those. Have you ever read Clive Cussler books? I'm pretty sure Clive Cussler probably did something with that. Yeah, he must have. All right. A roche montagne. I don't speak French, but I looked it up, and that's about how you pronounce it. Okay. Is when a hill has the misfortune of getting in the path of a glacier. Glacier advances and essentially scrapes this hill into a wedge. Okay, so it came from this direction, scraped off so much material from this hill that it makes this wedge shape now. Okay, so as it's kind of ramping up over the hill, it pushes up over this side and then kind of breaks and chunks off of the steeper side over here. This is a roche montagne. Glacial drift is a term that you will often hear associated with the sediment that is deposited from a glacier. I consider this to be a misnomer. It lends the impression that it kind of got washed there after the fact. It didn't. It was deposited there by the glacier. I prefer the term till, which is why that rock that you had in lab 3, tillite, right, was in there. It is a sedimentary rock that is made from glacial till that has been compacted together. Okay. Often characterized by sharp, jagged pieces because it is pulverized rock from a glacial deposit that has been compacted, and it's sedimentary rock. Okay. Stratified drift is what happens when you have seasonal deposition of sediment from a glacier. So let's say I have a glacier nearby, and in the warm seasons, it melts a lot, and so a lot of sediment runs into a nearby body of water, like a lake. And then you have a cold season, like winter. You get less deposition. And then warm, more deposition. Cold, less deposition. And so you have a thick and a thin and a thick and a thin and a thick and a thin layers of glacial sediment. That is called stratified drift. Also called varves. If you end up reading any literature about glacial stratified drift or till, oftentimes people refer to it as varves. And then we already talked about erratics. A moraine is what we call that assembly belts of sediment on our glacier. Okay? There are several types of moraines. A lateral moraine is one that occurs along the side of the glacial valley. So here and here. Okay? On the sides of our valley. What is this? As our glacier is moving down through the valley, it's scraping all that sediment off the side of the valley, and you're making piles of it on your glacier on the sides. And that's going to be your lateral moraines. You can see it in this picture right here. See that? That's a lateral moraine along the side of the valley on top of the glacier. Now let's see what happens when two glaciers meet up with each other. Here's a glacier moving down this way. Here's a glacier moving down this way with an arête between them. What happens when this lateral moraine meets up with this lateral moraine as the two glaciers converge and make one bigger glacier? The two lateral moraines join forces, but now they're in the middle of the glacier because there's that ice here and that ice here. This new larger glacier, these two lateral moraines are feeding into a medial moraine. Medial moraines are in the middle of our glaciers, where two lateral moraines have joined up and are now moving down that way. Okay? That is a medial moraine. Come on, camera. Thank you. And then the third type is a terminal moraine. This occurs at the very bottom of your glacier. Wherever your glacier is currently melting, it's depositing sediment along the front face of your glacier, right here. See that big pile of sediment here? That is a terminal moraine. You can see it here after the glacier has melted away. Right there, you see that big pile? Terminal moraine. Right there. So we have lateral moraines that run along the sides, medial moraines that are in the middle, which are the joining of two lateral moraines, and then your terminal moraine at the very bottom of your glacier, wherever the front is currently melting. Any questions about moraines? They're moving a lot of sediment downhill. Now, during an ice age or a glacial maximum, a lot of water is bound up in glaciers, which means sea levels fall. During the last glacial maximum, 18,000 years ago, this is what the coast of the United States looked like.
Florida's like
Florida's massive. Okay, actually, you can, and people have, go out off the coast of Florida, where there's hundreds of feet of water now, and you can find fossils of Pleistocene mammals out there because they were living out here in grasslands, okay, at that time. Actually, if you look at that map of the United States over there on that wall, and for those of you that are online, you can just Google, what is this called? Like a water depth map of the United States coastline. You see that white halo around the East Coast and Florida? That shows you currently submerged continental rock. Okay? That's continental mass that is currently underwater because we are in the hot period between glacial maximums. During glacial maximums, it's exposed. Okay? It's a lot. It's a lot of real estate. I won't say the thing. You want me to say it? Free real estate. Okay. So that's what happens during an ice age. All right. often associated with the onset of an ice age is an extinction. Also associated with warming. There's also usually some sort of small extinction. Okay.
The last extinction that's when most megafauna were hard hit by the glaciers melting. And it's debated if like humans had like a significant effect. The problem is the human population wasn't like absolutely massive, and it only hunted the megafauna low grade in a low grade way. So it's most definitely the melting glaciers that.
The extinction of the megafauna in North America is something that we do discuss in 1404 and possible causes for that. But there's usually some sort of extinction associated with a change this drastic in global climate. Okay. Now, another thing that happens as a result of the loss of all this ice is called isostatic uplift. If you want to understand isostatic uplift, all you have to do is think about wood on water. Does wood float on water? If I have a 1 foot by 1 foot block of wood and I put it in a water tank, will it float? Yes. Let's say 20% of it is above the surface. Okay. If I then cut half of that wood off, will it still float? What if I cut it off? What if I cut it while it's underwater and I cut off the amount that's floating above water? Will the rest of the wood that's left still stay below water? No, it'll bob up, right? So about 20% of it is still above water because that's its buoyancy ratio. The same thing is true for continental crust and mantle. When I add a bunch of weight to the continent right here, this glacier on top right here, this was a mile thick. This was a massive glacier. That's a lot of weight. And it actually pushed the continental rock deeper into the mantle because of all that weight. Geologically, that ice has disappeared in the blink of an eye. The Earth is 4.5 billion years old, right? 18,000 years is nothing, less of a blink of an eye, right? And so there ended up a giant depression right here where that ice pushed the continental rock deeper into the mantle. That depression is still there. We call it the Great Lakes.
I've actually been near the Great Lakes. It's pretty cool. It's like, when I went to Chicago, there, like, you can mistake it for an ocean. It's massive. Like,
the Great Lakes are really, really big. But here's the thing. Isostatic uplift. The mantle and the continent are rebounding. The pressure from the mantle and the buoyancy ratio of the continent above it is causing the continent to rebound upwards now that that weight is not there anymore. Which means that our continent, or our Great Lakes are getting pushed up. And since they are no longer able to be as deep, they're spreading out. Every year that passes, they rise up another inch or two. That doesn't sound like much, but a couple of inches can mean a lot of spreading water. As a matter of fact, Chicago is already starting to experience some minor flooding issues in the suburbs closer to the lakes. Give it another 50 or 60 years, and they're going to have some major problems, making Chicago even less of an appealing place to live, in my opinion. Sorry if any of you are from Chicago. I was not particularly impressed. I love their pizza, though. I got to say that. Chicago deep dish pizza is the best on the planet. I will say that.
Also, Field Museum is pretty cool.
The Field Museum is amazing. Yep. Okay. Okay. Already talked about all that. Okay. Now, where does glaciation come from? I'm just going to leave us on this note. Glaciation has been happening on Earth for a very long time. We have records of glacial cycles on continents going back billions of years. It's nothing new. We didn't start this trend of warm, cold, warm, cold, warm, cold. We didn't even start our current onset of warmth. 11,500 years ago, when our glacial cycle ended, humanity wasn't doing anything else than stabbing each other with spears. Okay? We didn't have fossil fuels. We didn't start the problem. We didn't start the fire, as that song says, right? The world's been burning since the world's been turning, right? That's how it goes. Okay. We've definitely added to it, but I've already talked about this. We didn't start it, okay? Actually, these cycles, as far as we can tell, initially started thanks to the advent of life on Earth. Yeah. Trees, plants, photosynthesizing organisms actually take greenhouse gases out of the atmosphere, crack them apart to build their structure, and then release oxygen back into the atmosphere, oxygen and water vapor. This process reduces greenhouse gases and increases oxygen in the atmosphere. That sounds great. That sounds wonderful. What does that do, though? Greenhouse gases retain heat in Earth's surface. They are larger molecules of gas, which means that it's harder for more radiation to escape our atmosphere. The more greenhouse gases, the hotter our atmosphere gets. The less greenhouse gases, the more heat escapes. Earth cools off, boom, bada boom, ice age. And so the first couple of major ice age cycles on Earth actually started because life was developing. They did it to themselves. They made their own extinctions.
Well,
Yeah.
I think watch one like in the early stages of life, the Cryogenian, where like a bunch of photosynthesizing, sorry, I can type today, microorganisms caused like or contributed to a massive ice age that reached to the equator.
Yeah, we call it snowball Earth when that happened. An ice age so big, there was so much ice on Earth's planet that everything but a thin strip of water around the equator was covered in ice. It's called snowball Earth. It wiped out almost everything on Earth. A few different types of bacterium survived, which continued to go on and create the sources of life that we have today. But it's nothing nearly that drastic anymore. Earth is found more or less in equilibrium. These days, best as we can tell, our glacial cycles seem to be tied to what are called Milankovitch cycles. Okay, Milankovitch cycles have to do with the way that the Earth turns. Okay, Earth experiences two types of movement on our passage around the sun. Our eccentricity, which is our elliptical orbit around the sun, which is on a cycle of about 100,000 years. Okay, we're doing this around the sun. The obliquity, which is the axis of our Earth versus the plane of our orbit. Notice how we are tilted, right? So we are at this axis right here, even though we are rotating this way around the sun. And the precession, which is the wobbling of our axis. We're doing this. So Earth is doing this around the sun as we go. And every so often, on average between 30 to 40,000 years, okay, we are at just the right point, furthest away from the sun, when more of our ocean is facing the sun and less of our landmass. So we're further from the sun, and therefore receive less radiation. Less of our landmass is facing the sun and therefore absorbing that energy. And therefore, at that furthest point, snow lines drop. More ice forms, more sunlight is reflected back out into space, and it's what we call a positive feedback loop. And this positive feedback loop is what causes a glacial maximum. Okay? That's what we believe causes it. It's pretty firm for the last 800,000 years or so that that's been the case. We're pretty sure about that. Before that, other stimuli seem to have caused them. It's only in the last 800,000 years that it seems to be tied to this phenomena, as far as we can tell in the geological record. Right. Okay. Any questions about glaciers or our lecture today? All right, well, I'll end it there and let's move into lab time. If any of my online students have questions, you can always email me.